magnetic field at all, this is going to have lower potential energy than this. And the difference between the two depends on how strong this field is. And so the graph looks like this. When there's no magnetic field, there's only one possible energy state for this thing, or if you like, these two are equivalent. But as soon as you apply a magnetic field, they separate slightly. Okay, so now, as soon as you've got a magnetic field, now there's two possible energy states for that proton. Magnetic in terms of the magnetism. Okay? So what an NMR spectrometer does is it picks a magnetic field based on how it's constructed. The stronger the field, the more sensitive the spectrometer, and the better the resolution of the spectra. We're not going to worry about that. All we're going to say is that each spectrometer has some value of the main magnetic field, and that causes the two different spin states to have slightly different energies. As long as there's a magnetic field, these two different spin states have slightly different potential energies. This one will have a lower potential energy than that one. Okay? So now, where will the nuclei be if these are the two, if we got a magnetic field equal to, see, if this is H0.
Sorry, which one's going to have more?
This one will be more stable.
And so because it's more stable, it's going to have lower potential energy. Right. So, okay, so that's the lower line.
That's the lower one. Now, where are the majority of the nuclei are going to be? When you're doing electrons, you always put the electrons in the lowest energy orbitals first. Okay? So you're going to be tempted to say, and you'll be partially right, that this state is the one that's going to be populated, and there'll be nothing in this state. But these two energy differences are so tiny that actually there's almost no difference in the population of the two. Okay? So now we've got these two energy states, and when you do spectroscopy, so when you shine light onto a compound and it absorbs the frequency of light, what's happening?
Vibrating.
Yeah, it's boosting electrons from a lower energy state to a higher energy state. And if the frequency of the light, the energy, matches the difference between those two states, it will be absorbed and push an electron from the lower up to the higher. And so the light that corresponds to this energy, this frequency, and this frequency only will be absorbed. So you get a spike in the spectrum. Same thing is happening here. If you shine light on this thing, and the difference in energy here between these, delta E, is equal to Planck's constant times the frequency of the light, you will absorb that frequency of light. So this is just like an electronic spectrum, except it's not electrons moving between energy states, it's the nuclei moving between energy states.
Because you're using a magnet.
Because you're using a magnet. You shine light in the absence of a magnet, you get no absorption. The stronger the magnetic field, the larger the energy has to be before it gets absorbed, and it'll move some of these from here up to here. So the principles of NMR spectroscopy are exactly the same as the principles of electronic spectroscopy. Light is absorbed when the system absorbs the light, and that only happens when the energy of the light corresponds to the difference between the two energy states.
It's not being a question, but with electrons, I think when you go to a higher energy, don't they do quantum leaps between the orbitals? So
Quantum leaps.
yeah, I think isn't it like if you go from like at 1s, for instance, and you go up to the next orbital, right?
Right.
It's that leap across orbitals. But anyway, it doesn't matter. But the point is, the energy increases about the atom. So when you're talking about
size of the magnetic field is different for every nucleus.
Okay.
Okay? And so if you drew the same diagram, say for a carbon-13, it would look like this. Because in carbon-13, these little magnets are stronger. So there's a bigger difference between this and that.
Okay. Well,
don't get it.
I guess the thing I was saying was that with electrons, I recall that there's actually a movement between.
Yeah, well, we talk as though there's a
With
movement.
protons, there's not movement, so there can't be movement, so that's what I was saying.
Yeah, but we talk about an electron going from one orbital to another.
Right. Is that
That's a
actually
fiction.
Oh, it's fiction?
That is a fiction.
Okay.
Remember that an electron is a standing wave.
See, I have this problem with standing waves and particles. Anyway.
You and every other physicist. Okay, what happens is the frequency at which that standing wave and the shape of the standing wave change when it absorbs energy.
Right.
The electron doesn't go anyplace. It just changes shape.
Does it just happen to act as a wave when it case?
Sometimes it's easier to think of it as acting as a wave, sometimes it's easier to think of it as acting as a particle. And what you gotta remember is it's probably the wave description that's more
No, yeah, they don't.
correct.
Okay.
Okay, so anyway, this is the idea, that if you put a compound, an organic compound, in a magnetic field, then all of the hydrogen atoms, each one has a little magnet, and when you put it in a magnetic field, each of those little magnets has two energy states, and if you shine light in there, whose energy just matches the difference in energy of those two states, you'll get an absorption. Yeah.
So you said carbon-12 doesn't have a split. Is that because there's equal amounts of it? Or
No, because it has it gets a little bit more complicated, but in some nuclei there are multiple. If there are more than one proton in a nuclei, there are multiple magnets, and some nuclei end up having zero magnetic field. They don't have a magnetic dipole. Other nuclei do. If this was not a magnet, that wouldn't happen.
Right. No. Yeah, I get that one. Why is carbon? But why does carbon-12 randomly have its own design?
Carbon-12, no carbon-12 nucleus has a magnetic field. Only carbon-13.
Okay.
Hold off that question until we get to C13 NMR in a couple of days down the road. All right? Okay, now, if this were all that was going on, NMR would be useless, because all of the hydrogen atoms in a single compound would have this difference, and you'd only get one absorption. Doesn't tell you anything. So here is our proton, but it's not alone. It exists in a molecule, and so there are electrons. There's a cloud of electrons around it. Okay? Or maybe that's for a neutral atom, maybe for, if it's bonded, say, to a carbon, the cloud of electrons might look like this. Okay? The idea is that when you put this thing in a magnetic field, not only is this affected, but when you put a charge in a magnetic field, the charge starts to move. And what happens is this cloud of electrons begins to rotate around the nucleus.
You get an electron.
And it rotates in such a way, and when you have a moving charge, that creates a magnetic field. So if this is the main field, if this is H0, these moving electrons create a very tiny magnetic field, and it's always in opposition to the main field. So this circulation of electrons creates a very tiny magnetic field, which is called HS. The S stands for shielding. Now, this proton no longer feels the full H0. It feels H0 minus HS. And because it feels a slightly different magnetic field, difference between the two energy states changes slightly.
Which is a slightly less frequency, which gives you,
That moves the peak. The degree to which this shielding field shields, in other words, the size of this shielding field, depends on just exactly how much electron density there is around this thing and how it's shaped,
which is the bonds and what it's.
which is
bonded to.
determined by the bonds, the chemical surroundings. Okay?
What is H0?
This is the magnetic field created by that huge magnet that you
So-
put the compound in.
Okay, so same thing as the book's B0.
Yeah.
Okay.
When I was learning this stuff, they used H, and I've not gotten that habit out of my head.
Okay.
So,
Okay? So there is, each proton in a compound experiences some shielding. And the amount of shielding is determined by what the chemical environment is around that proton. An easy example is, if this thing is attached to a carbon, the carbon is slightly more electronegative and will pull some of this electron density away. If it's attached to an oxygen, oxygen is considerably more electronegative than carbon. It pulls more of the shielding electrons away, and it reduces the shielding. And the technology here is sensitive enough that the NMR will detect each different proton, all the different shieldings of the protons in a compound, of the hydrogens in the compound. So if you're looking at the NMR spectrum of a compound, each different kind of hydrogen has a slightly different peak. Because this shielding field is determined by the chemical environment of this thing, this shift is called the chemical shift. And because the chemical shift always reduces the magnetic field, the chemical shift will always move peaks to the left. In other words, to lower field,
which is a smaller difference.
which is a smaller difference.
Okay.
Okay? So this proton experiences a smaller field than the H0, so it absorbs downfield.
Right.
Okay? Now, this difference depends on this. And this difference depends on that. So if you try to measure chemical shift in terms of how big that thing is, the chemical shift depends on how big the magnet is. So what they do is they take this shielding, divide it by that, and then the ratio of the two does not depend on what that is. And so the chemical shift is not in terms of how big a magnetic field, it's in parts per million. This is generally a millionth, roughly a millionth of that.
Oh, it's a ratio,
Yeah. So the chemical shift in parts per million for a given kind of hydrogen is exactly the same no matter how big the field. And so you don't have to standardize between NMR spectrometers that have different strengths of magnets in them. Okay. Chemical shift. Yeah.
Just, so you get that electric, or you get that, magnetic field, HS,
The shielding
or
field.
shielding field, you'll get that because the electron field around, the proton is.
The magnetic field around the proton is slightly smaller than that, due to the shielding of the electrons.
So an HO or VO
Hang on,
is,
Is it because it's irregular, or because it's no longer, what it normally is?
No, it is what it normally is. It doesn't change this at all.
Okay.
Putting this in a magnetic field only makes these electrons circulate around the nucleus. And that creates a small field in opposition to the main field.
And I missed something from why does it rotate then?
Oh, well, if you put a charge in a magnetic field, the magnetic field causes the charge to move.
Okay, that makes sense. And you don't get HS if it's not bonded to something else, or?
In order for there to be no HS, there would have to be no electrons around here.
Okay, so you always get. a
You
chemical-
always get some shielding.
Okay, so you.
How much you get depends on the nature of the chemical environment.
Okay, cool, that makes sense. I
That-
thought you weren't getting any chemical shift, and you
Oh.
had just like just the one
Yeah,
thing.
yeah.
And that was confusing, I didn't know why.
Okay, Jed, what was your question?
no, so then the V0 and H0, that's just it depends on the magnet you're using.
It depends on the design of the machine.
So that number could vary from machine to machine, but we're taking the ratio of the,
Of these two,
okay,
and that ratio stays the same no matter how big this is. This will always be exactly the same fraction of this, no matter what the size of the field.
okay, but we measure that ratio in parts per million?
Yeah,
So
this
then
is, this in general is a million times greater than that.
Okay, so then how do we relate this to the TMS?
We're getting there.
Okay, alright, so
I
you're
just want to make sure everybody understands where chemical shift comes from. What causes the chemical shift?
okay, so then to clarify that then, the more shielded it is, the smaller the ratio will be? Is that the right direction?
Yes.
The less shielded it is, or say it's just a naked proton,
It'll be
Then-
not shielded at
not
all.
shielded at all, then
You get the maximum energy difference.
that'll be like 1, right?
Okay.
Okay, and then the more
But
shielded it
the
is.
problem is, you can't put a sample of protons in an
Correct,
NMR spectrometer.
right, it always has something around it.
It's always got something around it.
Okay. So
Okay.
the more it has around it, the smaller that ratio is gonna be.
No, the larger. The more electrons there are shielding, the larger the shielding field.
No, the ratio. The smaller the ratio will be.
No, the ratio is this divided by that. This doesn't change. The more shielding there is, the bigger the shielding field, the higher the chemical shift.
Okay.
Okay, now,
I think,
grab one and pass it back.
okay, yeah, this is more shielding. That looks like.
Okay. First little detail. TMS. TMS stands for tetramethylsilane. It's just 4 methyl groups attached to a silicon atom. Okay? Those protons are extremely well shielded. And so they never occur. They occur to the right of where almost any other proton that you'll encounter is. TMS is also extremely volatile. So if you add a little TMS to a sample, it's easy to get it out. It just evaporates away. And so all chemical shifts are measured relative to TMS. So you don't have to calibrate.
And what was it again?
methylsilane, S-I-L-A-N-E. TMS is all you need to remember. It's a highly shielded proton that comes out at very low, this is just a sign essentially,
The zero, right?
0 parts per million. It's just an arbitrary 0 point.
So it'd be,
Put some of that in your sample before
You put that, yes, you put some of that in your sample
How
before.
smart is that?
Yeah, and then you will always have a little TMS peak, and you can always measure the location of the other peaks in parts per million downfield from TMS.
And we're, oh, sorry. I don't know. So, when you say the protons there, so we're talking about each methyl group, so all 12 protons, that's the most shielded we can get.
Actually, you could probably get more shielded, but TMS is a real convenient standard, partly because it's completely nonpolar, so it's easy to dissolve in organic compounds, and that's what we use this for. 2, its chemical shift is way up here. 3, it's got 12 protons, so you don't have to have much of it to get a good sized peak. And it's extremely volatile, so it's easy to get rid of it if you need to recover your sample. It's just a matter of convenience that we use TMS. It has just the right set of properties. There are other standards. You can't use TMS if you've got something that's fairly polar. There's another one called DSS. We don't get into that. All I'm telling you is this is just an arbitrary standard, an arbitrary 0 point. And all chemical shifts are measured in parts per million downfield from TMS.
Is there a way you can show us how those protons are so shielded? I don't know, pictorially, is there anything like that?
I guess what I would say is that both carbon and hydrogen are more electronegative than silicon. And so the silicon electrons get pulled away from the silicon, and they're out on the methyl groups, which increases the electron density in the carbons, so the carbons don't pull as much electron density away from the hydrogens, so the hydrogen have a pretty high electron density compared to other compounds that have hydrogen and carbon.
So the TMS is essentially, is like that baseline, like using, the chlorine, in IR, right?
No.
Using it.
carbon tetrachloride?
Oh, the carbon tetrachloride in IR is just a solvent that you can use that has no peaks in the IR except for that one way over on the right. It's just a convenient solvent. In IR, you need something else. You don't need a standard. In IR, you don't need a standard.
But it's just something, it's like a base point.
It's not a base point, it's a solvent that doesn't interfere with the spectrum. It's something, if you want to take some IR of a solid, for example, and you want to dissolve it in a liquid. Well, the problem is that if you dissolve it in a liquid, you're going to get peaks from the compound you're dissolving. You're also going to get peaks from the solvent, and that interferes with the IR, and how do you tell which is which? Carbon tetrachloride is convenient because it doesn't have any but one peak, and you know exactly where that one is. But the way they measure frequency in the IR is not relative to anything. That's the actual frequency. Okay? So, here are 2 peaks. A couple of things. This one is downfield from that one. What that suggests is there is less electron density around the hydrogens here than the hydrogens here. Easy to explain. This methyl group is attached directly to an oxygen. That pulls electron density this way and de-shields those protons. Pulls shielding electrons away. These 3 are more shielded because that carbon is this oxygen is 1 carbon away, and so it has a smaller effect on these 3 than it does on that one. So the relative position in the peaks in an NMR is directly reflective of the electron density, and it's fairly easy to look at a simple formula and say, okay, which peaks should be the farthest downfield, the least shielded, and which peaks should be the farthest upfield, the most shielded. The other thing about NMR is it's extremely sensitive and precisely sensitive to the number of hydrogens. You look at this and you say, okay, I got 3, 6, 9 of those and only 3 of those. And sure enough, this peak is about 3 times the height of that one. Okay. The truth is that it's not the height of the peak that matters, but it's the area under the peak. Now these peaks have roughly the same width, so the height works out. But if this one were much broader, it would be much lower, but still the area under the peak, under this one, would be 3 times the area under that peak. And what's nice about NMR is the machine calculates that for you too. It not only gives you this spectrum, but I'll show you an integration spectrum that shows you the relative area under each of those 3 peaks, or those 2 peaks. Okay? But the point of this is that chemical shifts are measured downfield from TMS. They're sensitive to the amount of electron density around the hydrogens, and the size of the peaks is proportional to the number of hydrogens that make that peak up. Here's another one. Which peak goes with which carbon?
Yeah, I mean,
So the little, I don't call them ender peaks.
Oh,
does
if,
that make any difference?
no. This, if an NMR spectrometer is working properly, when the pen comes up, it goes down and it goes.
Is the y-axis the orbits?
Yes. You look at this thing and you say, okay,
So we're looking at A, B, and C,
A,
right?
B, and C. Which peak goes with which set of protons? Here's A. It's directly connected to an oxygen. This one, C, is connected to a carbon that's connected to an oxygen. And this one is connected to 2 carbons, which are connected to oxygens.
Would it be?
Which
A,
is the most deshielded? Which has the least electron density?
the methyl? On the
You would
A?
expect it to be the methyl, right? Because that's directly connected to an oxygen.
But,
No but.
okay. You said you
You'd
would
be right.
expect, okay.
You would expect that, and you'd be right. This thing and this thing are both connected to carbons, which are connected to oxygens, but this is connected to only 1,
So it's gonna be
and this is
less.
connected to 2.
So it's just A, B, C then?
Yes, so this would be B, and this would be,
C? Would it?
Why is C smaller than
Yeah, it would be
Shorter.
just B.
no, A, yeah, this one, this is
A.
A. This is C, because it's next most shielded. This one is B, the one in the middle.
Wait,
No,
No.
C is
No,
the
no, no. C is the most shielded, so this would be C, this would be B, this one here. And that also corresponds to the relative size of the peaks.
C
There-
is more shielded
pardon?
than B?
Pardon?
C more shielded than B.
Because B's got 2 oxygens right next to it.
This oxygen is partially positive because of that oxygen. So this partially positive carbon is pulling electrons away from this. This thing is twice. So this thing is going to be the most shielded, that the least shielded, and this in between the 2. And sure enough, there are 3 hydrogens here, 3 hydrogens here, and those are the 2 big peaks. Only 2 hydrogen here, and that's the smaller peak.
The more shielded it is,
This.
the more,
So in other words, the more shielded, the less shift.
Yes. Remember that TMS is highly shielded.
Right.
So it is A, B, C, from left to right.
Yes. A, B, C.
And you said that the relative,
That's what I had it and then I switched it.
you said the relative height makes a difference because we're looking at 3 protons versus 2?
Yeah, I'm going to speak loosely of the size of the peak. Just keep in mind that what you're really talking about is the area
Integral.
under the peak.
Right.
And so the height of the peak is not reliable. You notice that that's 3 and that's 3, but these two are not of the same height.
Right.
This peak is a little bit wider than that one,
Takes away.
and so a little bit shorter for the same area.
So can you say shielding is just proportional to the shielding?
Yeah, shielding is dependent on the, pardon?
Not as much absorbance as just.
Are you talking about the size of the peak or the
Well,
location?
I'm just saying that the height doesn't matter as much because that's measuring the absorbance as opposed to.
Yeah, this thing, where the peak occurs, depends on the degree of shielding. How big the peak is depends on how many hydrogens are contributing to it.
So the farther to the left, the less shielding,
That's correct.
The more naked it is.
which means those protons are more exposed.
Yes.
Because there's something very strongly electronegative pulling
It's
away,
pulling
the
away.
electron shields away, right?
Exactly.
Shields
So
down.
again, why is A and C not of the same area under their peaks?
They are.
They are.
They are the same area, but the point is, it's the area that matters, not necessarily the height. So you can't go by the height of
But
the
the
peak.
area's the same.
But depending on how wide the peak is.
Yeah. If I had a peak that was real wide, it wouldn't have to be very high to get the same amount of area.
I know what you mean though, Tam, because it looks like A is wider than C.
It looks
Yeah.
like A is wider than C to me, but I didn't integrate it, so.
Well, yeah, okay, to answer that, go down this far from A. You compare that width to that width.
That's what you're supposed to do. But then.
I'm just trying to justify this in your head. Trust me.
Okay.
Okay.
So the weird,
I believe you.
Thank you.
Are we just about to see an integrated one?
Yeah, you're about, right after this one. Now.
That's pointing to which one's which, right?
Yeah, it's showing you which one's which.
And again, here we're looking at single protons, but why are they B's for the up and down one and C's on the far left? Is it because of the
They're
methyl
not
groups?
equivalent.
The methyl group has some pull on it?
No. Well, yeah, these two things, these two sets of protons are entirely equivalent,
Right.
okay? These two are entirely equivalent, and these two are entirely equivalent, okay? These two and these two have very, very similar chemical environments, so they have very, very similar chemical shifts. You'll notice that this peak is nice and sharp. Here's that little ringing pattern. It's not here. Because this is really this peak sitting on top of that peak.
And so instead of going up and smacking that down and
Yeah,
getting.
it goes up and then down.
And kind of like,
Okay? Now, there's another thing that's odd about this thing. You remember where the methyl group attached to an oxygen was? It was down around 3 parts per million. Okay? There's no oxygen here, so why are those protons so de-shielded? And the reason is because of the electrons in that ring. Those electrons are free to rotate because the lowest molecular orbital on this is just a ring, looks like a donut. And so what happens is, in an aromatic ring, these electrons, the pi electrons, circulate very strongly, and since these hydrogens are outside that circulation, the magnetic field they feel is de-shielding. So hydrogens attached to an aromatic ring are extremely de-shielded, not by something that's electronegative, but by what's called the ring current.
the re-what?
Ring current. It's the rotation of the electrons in that aromatic ring.
Maybe conventional.
So then is C slightly more downfield than B, ever so slightly?
I would guess that B is slightly more downfield than C.
Oh, that's what I meant, because B would have the effect of the methyl groups.
Yes.
Okay.
Sort of.
Okay, now, here is a spectrum that shows the integration. This is the NMR spectrum that you normally see. But then what you do is you put, electronically, you put the spectrometer into integration mode. And what it does is it goes along flat, and when it comes to a peak, it goes up proportional to the area under the peak. So this is the integration curve. It doesn't tell you the exact area, just the relative area. So you measure that height. That turns out on that piece of paper to be 4.6 somethings. And this is 13.6 somethings. And if you multiply 4.6 times 3, you get 13.8. Very close to 1/3 of that.
So you just put the smaller over the larger, and then you'll get the
Yes.
fraction between the two.
That's exactly right. What you do is you'll divide this by this, and what that tells you is there are 3 times as many protons here as there are here.
And that's all that'll tell you though, right?
That's all that it will tell you, the relative numbers of protons. Okay. Now that's kind of cool.
But
I'm going to explain this in detail, why this arises. But let me tell you at the outset what you need to remember to interpret the spectrum. This proton is all by itself. These two are entirely equivalent. They have exactly the same chemical environment. So we expect the peak for those two to be twice the area as the peak for this one. But these peaks are split. This one into a doublet, this one into a triplet. What that tells you is that since this is a doublet, whatever the proton is here, there's one proton on a neighboring carbon. These 2 protons have one neighbor. And that neighbor splits this peak into 2. This peak is split into 3, a triplet,
Because it's split by the
because it has 2 neighbors. So what you can tell from the splitting patterns is how many hydrogens there are on neighboring carbons. So I know not only is this thing more de-shielded than this one, but this thing has 2 neighbors, this thing only has 1 neighbor.
so the neighbors equal peaks minus 1? Or no?
Peaks plus 1. Oh, peaks minus 1, yes. Peaks minus 1.
So 3 peaks equals 2 neighbors.
3 peaks is 2 neighbors, 4 peaks is 3 neighbors, 5 peaks is 4 neighbors, 5 peaks is 3 peaks is 2 neighbors, 4 peaks is 3 neighbors, 5 peaks is 4 neighbors, and so on.
And what's a neighbor again?
It is a hydrogen, so these hydrogens are on this carbon, and so the neighbors are hydrogens on the carbon next door.
Oh, okay.
Well, what does this have to, does this have anything to do with that n+1 thing?
Well, I mean, the rule is n plus 1. So the number of hydrogens plus 1 is the number of peaks the thing is split into. So one hydrogen.
It's going the opposite way than
Yeah,
we've been
one
doing.
hydrogen, 1 plus 1 is 2, and that's split into a doublet. This peak is split into a doublet. This thing has 2 neighbors, 2 plus 1 is 3, so this is split into a triplet. And you'll notice that these things are about the same, but this doesn't look like the same. no neighbors.
You're gonna have one peak.
One peak. One neighbor.
Double it.
You'll have two peaks, but they'll be equal in size.
Well, the example really wasn't that equal, was it? Or are we talking about area,
We're talking about area,
not the height?
not the, yeah, the height is deceptive,
Okay,
okay? Two neighbors, three peaks, the middle one will be twice as high as the two outer ones.
so this is that Pascal triangle.
This is Pascal's triangle. You have three neighbors, okay? And the way you can, if you're not familiar with Pascal's triangle, each of these numbers is the sum of the two just above it. So the next one, if there are four neighbors, we'll get a 1, 4, 6, 4, 1. This is a singlet. This is a doublet. This is a triplet.
Quartet, I think it is.
Quartet.
And when do you use quad and when do you use
Pentuplet.
tetra?
And so on. I never have figured that out.
That sounds right.
The book says quint.
Oh, sorry, quintuplet.
Quintet.
Quintet?
Quintet, sextet, and a septet.
I'm obviously using old. Split into 5. Quintet, sextet or sextuplet?
Sextet.
Sextuplet? Okay, so this is the pattern. That's what you need to remember. Okay, now I'm going to show you why this comes out this way, and then I'm going to. Let's suppose we have this situation.
Not twice as big, twice as much area. Yeah.
Okay, and there's other things on those carbons that are not hydrogens. Okay, these two things, maybe in the compound we were just looking at, these are bromines. Okay, which is why this one is farther this way and that one is farther that way. Okay, now, let's consider the peak that those protons make. This one, remember, is a little magnet. Okay? And in roughly half the molecules, the magnet points up. In the other half of the molecules, it points down. And so the field that this thing is feeling is the H0 minus the shielding field. And this is called the spin-spin coupling. It also feels, these also feel that little magnet. And so there's another splitting field in half the molecules that adds to the main field. In the other half, it subtracts. So half of these things are moved a little bit this way, and half of them are moved a little bit that way. And this one, these things end up being a doublet. 50-50 doublet, because half of these hydrogens are up, half of them are down. Let's look at that one. Each of these two hydrogens is a little magnet. Each one of them has a 50-50 chance of being up or down. So the possibilities are, both of these are up. Or, one of them is up and the other one is down. Or, the other, one of them is down and the other one is up. Or, both of them are down.
And the two in the middle are not equivalent?
Yes,
They are equivalent.
1/4 of the molecules look like this, 1/4 look like this, 1/4 look like this, 1/4 look like this. These two things, those field cancels, so there is no splitting field. 1/4 of them, and the other quarter this way, so you get 1/4 of them like this, 1/4, 1/4, or half of them like that, not shifted either way, and 1/4 of them more shielded. There's your 1, 2, 1 triplet. That's basically where those splitting patterns come from. If there were 3 neighbors, okay, there's 2, 4, 6 possibilities. Okay? 1 where they're all up, 1 where they're all down, 3 where 2 are up and 1 is down, and 3 where 2 are down and 1 is up. Are not equivalent, so you get a quartet. 1, 3, 3, 1. Okay, that's the where that comes from. All you need to know is this and Pascal's triangle. That's all you need to remember to interpret spectra. So, does that make sense?
Better. So is that 6 or 5 peaks there? On, for C? On the graph.
Oh, for here, I gotta warn you that there is sometimes when you have lots and lots of splitting, the peaks on the outside are always the smallest. And sometimes if there's a lot of splitting, they get so small that they tend to disappear.
Okay.
We have this one next to the carbon that has the oxygen, that pulls electron density away, but there are no hydrogens on this carbon. So these 3 have no neighbors. This one are farthest away from the oxygen, so they will be the most shielded. They have 1 neighbor. This thing is split into a doublet. This thing is next to a carbon, double bonded to oxygen, and it's also bonded to 2 other carbons. If you compare this to this, carbon is more electronegative than hydrogen, so every time you would replace a hydrogen with a carbon, that moves the peak about 0.4 of a part per million to the left. So this thing is more de-shielded than this thing. That's here. And it has 6 neighbors. So it's split into a septet.
A little oscillation to the left of that, the big piece is that one?
This oscillation here?
No, to the left. That's C.
Yeah, that is C. That's this one, split into 7 little peaklets.
But I don't see the sun.
And you don't see all 7. Okay? And here's one other feature that I'll point out about it. This thing is unsplit. These protons are unsplit. Okay? These 6 protons are split by that one. And because they're split by a peak on their left, the left-hand peak of the doublet is larger than the right-hand peak of the doublet. These resonances from that proton, they're being split by the protons in that peak. And since they're being split by protons whose resonance is to the right, the peak on the right is a little larger than the peak way over on the left, which you can't see. In other words, the heights of the peaks are a little higher on the side nearest the peak of the protons that are splitting them. Which is why you see this little peak, but not that one. 1, 2, 3, 4, 5, 6, and you can't see 7. But you'll notice if you look at these 2, this one is higher. You look at these 2, this one is higher. The ones that are on the side nearest to the peak of the proton that is splitting them are a little bit higher than the ones on the opposite side. Yeah.
Dr. Arda, this is actually on page 583, figure 1326. And they blow it up so you can see all 7 peaks.
Oh, yeah. This is, typical. When you take an NMR spectrum, you have to adjust the size of the spectrum so the largest peak stays on field, stays on the paper. But that makes this peak so small, so what they do typically is they'll go back and they'll just redraw this, but they'll reset the spectrometer to make it the peaks much bigger and spread way out. And so you'll often see a little peak like this blown up so you can see what it looks like. And when you see it here, it's fairly obvious. 1, 2, 3, 4, 5, 6, 7. And in each case, the peak closest to the one that's splitting them is a little higher. This one higher than that. This one higher than that. This one higher than that. So they essentially point to the peak of the proton that's splitting. Okay, on Monday, we will start trying to identify. Oh, that's kind of cool. On Monday, we'll start trying to take NMR spectra and determine the structure of molecules based on the NMR spectra. And after we get a little practice at that, we're going to do it with molecules, and the only thing we'll have is an IR